All right. Ladies and gentlemen, let's get started, please. There's nothing out right now. She's hot. She's using her time effectively. Full disclosure, even though Nick is not here to talk us into it, we are currently recording. Right? So we will record this, post it for people who aren't here. Like Nick. Yeah. All right. If you have not done so, something to write with, the outline that I gave you last week on mechanics, and then the problem set that said describing motion, mechanics describing motion, it's one that had all the dots. All right, let's start with calendar. I made some changes to the calendar. First, lab. Lab is due today. If you have finished it up, answer the questions, get it turned in. If you have not finished up your data collection, or if you finished up your data collection and saved it on a jump drive, and you have to analyze some more, get that done sometime, either today or tomorrow, so we can get that taken care of. Today, did test review. We're going to review some of the things we talked about last week. Then we'll get into our last question, and that question deals with acceleration. And we'll introduce the topic of acceleration today, talk about its definition, maybe talk about a couple of applications. We'll go from there. Tomorrow, at the beginning of class, I wanted to go over some more acceleration things, some homework type stuff, questions from the homework, but also a couple other questions. Okay. Then your quiz. I originally had the quiz way back on Friday, then I had it labeled here as take home. That quiz is going to happen in class tomorrow. Okay. It is an open note quiz. You may use your outline. You may use any of the things we've talked about over the past couple of days. Okay. So we'll take that quiz in class. Then, depending on how much time we have, we're going to start looking at the relationship between velocity and acceleration. There's a couple of sheets that problem sets that we do. Look at that, how the numbers change, and what does it mean if you have this acceleration. And we'll go from there. Okay. We'll do that end of Tuesday and into Wednesday. Next quiz is the relationship between velocity and acceleration. We'll see from that quiz if it's going to be Thursday or if we push it back to Friday, depending on how it is. Okay. Then, starting on Thursday or Friday, we'll talk about our next lab, which deals with graphs, graphs of time and position, graphs of time and motion. We'll talk about those when we get there. We will collect data together one day in class because just a little fast because we don't have a block this week, so it's a little faster if we do it together. So we'll collect data together one day this week. Then you'll have another day to work on it in class. We'll see about going to the library. I got to kind of see where we end up. So anyway.
Will we do it Friday?
No, I'll move that around. Sorry. I forgot to move it after I was rearranging things this morning. It's not going to be due on Friday. So probably more like Monday or Tuesday. Next week. Do you have tests on the schedule for Wednesday of next week? I really don't think it's going to be that day. It's probably going to be more Thursday or Friday, maybe both, because we are on short periods next week, so we might have to split that up over 2 days.
Is it a big test?
It's kind of big. It deals with all of the intro to mechanics stuff. Not quite as big as that test you just took, probably, but probably more like in the 30 to 40 range. So, but that's what the calendar looks like. Are we good there?
Yeah.
Okay. All right. Let's start off with this. Last week, we introduced this idea of mechanics, mechanics being the study of motion. We said that there's 4 questions that we want to know about an object in order to calculate, in order to accurately describe its motion. So the first one was, where is the object? That was the first question that we wanted to answer. And we talked about the idea that that question can actually have a couple of different answers, depending on what we actually want to know. There were 3 terms that we discussed that related to the where is the object question. What were those 3 terms that we talked about that were related to where is the object? Here's what's one. Position. Position tells us what, Chris? Where it is at that moment in time. Okay? I'll pause 1 second. On this sheet here, right? The first question on the first side says write the value of the position vector at t equals 5 seconds. Let me do this. Grab this and bring it into where I can right. And we talked about that the answer to that question was at 5 seconds, so we looked at 5 seconds. There it is, and so we said that the position vector was 4 meters, right?
Yeah.
Okay. We could either say it was 4 meters east, or 4
Right.
meters right, or positive 4 meters. Because we said that position was a vector quantity. And vector quantities tell us what? Well, not necessarily how fast, but more generally what? Magnitude and direction. In this case, Alex, this quantity for position isn't telling us how fast. It's telling us how far, right? It's 4 meters away from the reference point, but in which direction? Well, the positive direction, which in this case we called towards the right. Okay. Position was one thing that answered the where's the object question. Allison, what else did we talk about? Displacement. And Allison, what did displacement do for us?
Change of direction.
How about the change in position? All right. So we said that calculating displacement looks like this, right? X final minus X initial, the final position minus the initial position. And that was question number 2 here, right? We look at where it started at 3 seconds, right? We look at where it ended up at 8 seconds. The final position we said was positive 11 meters minus the initial position, which was positive 2.5 meters. And we ended up with a displacement of positive 8.5 meters. Sound familiar? And then we said there was one other term that answered the where is the object question. What term also related to where is the object? Go ahead.
Distance traveled.
Distance traveled. And distance traveled did what for us?
Told us how far.
The total path that we took, right? And we discussed that with this guy, right, and his trip to the gas station and back. And so we talked about that we used this as an example of the difference between distance and displacement. Okay? Does that sound good? Awesome, go ahead.
On the notes,
Yep.
after distance traveled,
Yep.
scalar quantities tell you, and I didn't get that one.
Okay. Scalar quantities only tell you magnitude, or only tell you how much. Okay? Now, in the case of distance traveled, be how much specifically would be how far, right? That's what distance traveled will tell you. How far did you go? It doesn't really matter if you go in a circle or if you end up back where you started. It just wants to know how far did you go. All right, good on where is the object? Okay. The second question we talked about. What is the object doing right now? And the answer to that question, once again, we said there were 2 answers to that question, right? Speed and, say what else? And velocity. So speed and velocity. What did we say were the 2 big differences between speed and velocity? Well, actually, there's one big difference between speed and velocity. Chris, what is it?
Velocity, velocity is displacement, but it tells you where you're going, in which direction.
What kind of a quantity is velocity?
So the delta over time.
That's how we calculate it, Alex. What is it? A vector. So velocity is a vector quantity, which means that it has to tell us 2 things, right? What does velocity have to tell us? We calculate velocity by taking the displacement over the time. The velocity tells us the ratio between the displacement and the time. But what does the velocity actually tell us? It actually sort of indicates 2 things for us by the fact that it is a vector quantity. It tells us how fast, but also tells us which way. Does that make sense?
And speed, that tells us how fast.
Because speed, Sam, is just a what? Is a what's the name of that one? It's not a vector, it's a scalar. So it only tells us how fast. Okay. With that being said, let's go back here. Okay, to this problem set. Question number 3 says, what is the average velocity of the object between 3 and 8 seconds? Now, Chris, Miriam, if we're calculating the average velocity, what 2 things do we need to know in order to calculate the average velocity? The displacement and the time. Right? So the average velocity is equal to displacement over time. Okay? If we look at the previous question, question number 2, right? Actually, on Thursday, right? We talked about the idea that we can break this down to make the formula for velocity look like that, right? Because at top is we're just calculating displacement. In number 2, what did we calculate? The displacement between 3 seconds and 8 seconds. So if number 3 is asking us for the velocity between 3 seconds and 8 seconds, what can we plug into the top of this fraction? The positive 8.5 meters, right? What's going to go on the bottom here? 5 seconds, because that's the amount of time that goes by. You take 8.5 divided by 5. Sam, can you run that through for us real quick so you can save your calculator out?
1.6.
And that should give us 1.7 meters per second. Yes, Allison?
I don't understand how you like that.
Okay. Allison, first, do you get this? What am I calculating on the top of that fraction? Because look, right? We calculated displacement that way. So I just took the formula for displacement and substituted it into that formula. Okay? In this case, right? This is the final position. This is the initial position between 3 seconds and 8 seconds. We did that the other day to calculate the displacement, right? So then I just plug that number in the top of that fraction there.
Oh,
Okay.
so is that like x times x?
Yep.
It's the same thing as
Because Allison, in these 2 questions, the time frame over which that's occurring is exactly the same. So yeah, it is. We use the answer for 2 to answer 3. Okay? And then the time, we just look at the difference in the time. That's how we got 5 seconds. Because it's between 3 seconds and 8 seconds, right? Alex, go ahead.
I still don't get how you're guessing that shit. Wait. Oh, okay. Oh, I was looking at the wrong one. Okay.
Wait, so then when you're doing like a problem, like the PE, the little E under it, the elastic potential energy,
Yeah.
when it has the little triangle with the X, that means you do that formula,
Yep.
and then you like.
Yep.
Okay.
One thing to finish this problem off, number 3. Okay? Is this the right answer? It's number 3. Not quite, right? Positive 1.7 meters per second. Because that now indicates not only how fast we're going, but also which way we're going. Okay? Say again. We could put the direction, Miriam. Like if you put right here, that would be fine. Okay? Although when we do the math calculations, it's usually better if we use positive for one direction, negative for the other direction. All right, good so far? Okay. Back to mechanics. 4 questions, right? Where's the object? What is it doing now? The third question. What will this object be doing in the future? So if you go to your outline, you could probably figure out that the answer to that question is called what? Acceleration. Okay. So, I forgot to change this, so here's the formula. If you want to write it down right now, you can, so it's not distracting you. You can kind of get rid of the average there, that's fine. Just same idea. All right, definition. Acceleration is the rate at which velocity changes. The rate at which velocity changes. Yes, Alice?
Wait, is acceleration tomorrow?
Yes. That's why I wanted to go over it a little bit more. So we're not going to take the quiz right at the beginning of class. We're going to take it more like in the middle because I wanted to go over some more acceleration topics with you. All right, so two things. First, if this is what acceleration is defined as, that means that determining the acceleration is going to depend on two things, right? What are the two things that determining acceleration is going to depend on? So, this part here, right? What does it say at the bottom here? Velocity changes. That's the important part, okay? That's the delta V part here, right? Sam, because you were talking about it before. What did we say the delta meant? The delta means change, right? So delta V on the top of this fraction is Allison representing change in velocity. The fact that it's a rate, right? We talked about last week that if we define something as a rate, what does that mean? Some time of time, or it's over time. And there it is, okay? So the change in velocity over time. Okay? Good there?
So how would you
Let's keep going. Acceleration. The reason why it answers that third question, what is it going to be doing in the future, is because acceleration tells us about the change in the motion. Velocity says, what is it doing right now? Acceleration tells you how much is it changing what it's doing right now. How much does the motion of the object change? That's what acceleration tells you. It's kind of a tricky concept, and we'll get into it a little bit more over the next couple days. Okay? As far as calculating it goes, you already wrote down the formula, but acceleration is the change in velocity divided by the total time. Calculate the acceleration, you need the change in velocity divided by the total time over which that change occurs.
What goes into the unit part after the formula?
That's where we're going right now, Josh.
You're on how's the auto shift?
Alright, so there's our formula, right? Units-wise, what are we talking about in the top of this formula here? Okay, this is going to be meters per second. Because even if we talk about the change in velocity, right, it's still going to be velocity minus velocity, so it's still meters per second. What goes on the bottom of this fraction? Seconds, okay? So the unit for acceleration is actually a compound fraction. It's meters per second. Because, what did we say the definition of velocity is? Allison, how much what? How much velocity changes. So if we have a unit of meters per second, right? The velocity changes by a certain number of meters per second every second. This is a difficult concept. Okay? Now, the fact that it is a complex fraction doesn't mean we generally write it that way. Okay? Here's the complex fraction here. I'm going to do a little math. Okay? If I multiply the bottom of that fraction by 1 over seconds, you don't have to write this down just yet, but if I multiply the bottom of this fraction by 1 over second, what happens on the bottom here? The seconds cancel. But I can't just multiply the bottom of that fraction by 1 over seconds if I want it to be the same thing. I also have to multiply the top of that fraction by 1 over seconds. Okay? When you do this, right, we're just multiplying fractions again, so you end up with meters over s squared. So meters per second squared. That's generally how you will see the unit for acceleration written as meters per second squared, which is the same thing as this, meters per second. Just a little easier to write. All right, are we good there? Okay. couple more conceptual things. First, acceleration is a vector quantity. By now, you should be able to tell me that that means that acceleration has to tell you two things, right?
Magnitude and direction.
Magnitude and direction. When we said magnitude is sort of a general term for how much or how big. In this case specifically, the magnitude on the acceleration is going to tell you how much does the velocity actually change. The direction is going to tell you which way, which we'll see in a second. Physically may mean that one thing happens versus another thing happening. So it has magnitude. How much does the velocity actually change? But then it also has direction. Which way is the velocity changing? And we'll see what that means here in hopefully just a second. All right, we got those? Good so far? Okay. If we go back to the definition of acceleration, right? The rate at which velocity changes, or how much is the motion of the object changing. There are three physical motions that fit the definition of acceleration. One of them you guys think of as acceleration. What's one physical motion that's out there in the real world that we generally think of as acceleration? A car, more specifically, what's happening to that car? Going faster, all right? That's generally the first thing that we consider to be acceleration, okay? That guy's cliff diving there, right? Okay.
What is that something jump into the water?
Yeah, you jump from the top of a cliff into the water.
Yes, I don't know.
Never like to that extreme, but like one time when I was whitewater rafting, they stopped the raft. There's a cliff. It was probably about like as tall as like this window to the ground. So it was like 25 feet or something. It was pretty cool.
I went whitewater rafting and this guy's feet turned red. It was so cool. It was really gross. He was like showing me and I was not interested.
I've been whitewater rafting 4 times.
I went once and I was scarred.
Good time. I keep going back. So
Where do you go?
usually the Western States.
Don't in Mexico isn't there a lot of cliff?
Yeah, they do cliff diving in
Well, I think
Mexico.
when the guy stopped.
Well, he's diving,
Diving.
so you know.
That was
And whenever I use this picture, and people ask this, they're like, does he actually clear those rocks?
Yeah.
The answer is, I don't really know. To make myself feel better, I say yes, that he's clearing the
Have
rocks.
people
I don't
died
think
from
so. It
cliff
seems
I don't
like
think so,
the last.
But, back to the discussion at hand. This is a kind of acceleration. This is like when you press the gas in the car. What happens to the velocity in this situation?
becomes fast.
It becomes faster, and that is a change in velocity, and that is acceleration. However, if our definition of acceleration is a change in velocity, or how much does the velocity change, there are two other things that fit the definition. What else could be considered acceleration, Chris? Slowing down is also going to be a form of acceleration. Okay? So this big boulder is slowing down. Hopefully the rate of this acceleration is bigger than the rate of this acceleration.
Okay. Look, it's going down the hill.
Yeah, I didn't draw that picture that way.
You can.
I mean, you could, well, actually, here it is.
Maybe it's going up a hill.
So it could be going up the hill.
I think that's the hill.
Now, let's do this, okay, just to clarify. This is a form of acceleration. It fits the definition. Sam,
Yes.
what was our formula for acceleration? How did we calculate acceleration?
Equals delta V divided by T.
Okay. In order to calculate delta V, Sam, we said before, what does the delta mean?
Change.
Change, right? And in order to calculate the change in anything, what do we need to know?
Like the force
The before and after. Where does it start and where does it finish, right? So in this case here, we could spread this equation out to look a little bit more like this. This is all the same equation. I just, put it out a little bit farther. Delta V is V final minus V initial. Where does it end versus where does it begin? In the case of slowing down, what would you see about V final versus V initial? How big would V final be versus V initial if we're slowing down? The final would end up being smaller than the initial. If that's the case, what happens to this fraction? If you have a smaller number minus a bigger number, it turns negative, right? So slowing down, a lot of times, we can refer to as negative acceleration. Please don't use deceleration. It's just not really a word, all right? Okay. Slowing down is negative acceleration, a lot of times. That means that speeding up, right, in the case of speeding up, what would we see about V final minus V initial? V final is bigger than V initial if we're speeding up, so that means positive acceleration. Okay? Yes, sir. Go ahead.
How do you get the V final?
I got to tell you somehow, or we have to measure it somehow. Okay? Right now, we're just talking conceptually. Okay? But Chris, does it make sense that if something is slowing down, the final velocity, whatever it is, has to be greater than the initial velocity, or sorry, smaller than the initial velocity? Technically, it's negative. Okay?
So in this case, would you have a negative in front of the number itself?
No. They're both positive velocities, because what does the sign on velocity tell you?
It's changing.
Which direction it's going. So Alex, in this case here, the boulder is still going in this direction. So that means that the initial velocity here, let's say, would be positive 10 meters per second. I just made that number up. Okay? Then over here, it has slowed down to 8 meters per second. But which way is it still going? It's still going positive. So when I take these numbers and plug them into this formula, I have positive 8 minus positive 10, right? And I end up with a negative 2 then. Does that make sense?
But it's still positive.
But it's still, well, the velocities are still positive, but the acceleration is negative.
So would the final answer be negative 2 meters
Per second squared.
Or would it be plus and then you...
No. Because we're calculating two different things, right?
So then, for that to, like, for what he's talking about, that's like, no.
Yeah. Miriam, you threw it out there. What else could this guy do in order to get out of the way of the boulder? Just move which way? To the left or right? You go up. It could go up as well. The third kind of acceleration is changing directions. Because on a Ferris wheel, what do you do the whole time? What are you doing the whole time when you're on a Ferris wheel? You're accelerating. You are changing directions. Okay? So,
because you're like...
because we said, as we talked about before, velocity is a vector quantity. It has directions, right? If you go in a different direction, that's a change in velocity. Okay? All right, on the calendar. Let's see if I can get this in before the bell rings. On the calendar. Nope. Just for the recording, okay? Here's stuff from the book for tonight. This is all conceptual stuff about acceleration, like we talked about today. We'll do some more conceptual stuff at the beginning of class tomorrow, then we'll take a quiz.
That's